next one, reducibility, chapter 5, that's about 25 pages. So, you know, smallish chapters. Okay, so we'll use a terminology that we'll use for the next couple of chapters. It's pretty simple. It's just like this is a description of a language. Okay, P, just some member of the language, so some presumably a string. And I'm hinting at what we'll be talking about later sessions on the board. So, and then, well, since it's an infinite set, we can't just list all its members. Remember, there are two ways to write down a set. One is you just list all its members within wiggly brackets. Obviously, that only works when the set is small. Otherwise, it's not practical or impossible, infinite. And the other way is to put a vertical bar like this and then give a description, of the property, to list the property or properties this element has to have to belong to that set. So obviously this infinite set will have to be of that second kind, the descriptive kind. See? So here's a description of the property that this element P has to have to belong to the set D, and that is it's a polynomial with an integral root and at least one integral root. Okay, so this set D is the set of all polynomials that have integral roots. Okay, so we'll use this description of a language. And in fact, we've been doing it quite a few times. We just haven't, Sipser hasn't spelled it out explicitly, he's just been using it. So we've been picking it up just by exposure, by osmosis, if you like. Right? So we'll use this description of language to will help us when we're trying to see whether this particular language is decidable. What does that mean? It means that a language is decidable if there's a Turing machine that decides it. And what does that mean? A bit of revision here. A Turing machine decides a language if each string in the language, remember that's all a language is, just a set of strings. Okay? So a Turing machine decides a language if it accepts or rejects each member of the language, in other words, each string. So it accepts or rejects each string from, for all strings. And so it accepts the strings that are in the language and rejects any other. So that's to decide. Now, from comments this session and the next, I think I'm now clearer on the distinction. Could you remember me querying this, posing it as a question in an earlier session? What exactly is the difference between Turing decidable and Turing recognizable? Well, I felt that Sipser did not spell that out too clearly, but now it's starting to gel, crystallize, just from his comments. If you use this kind of thing, so you've given a description of what property a string has to have to belong to a language, and then a Turing machine can then decide that language. Recognize. I'm talking about the distinction between recognizing a language and deciding a language. Okay, because they're not the same. So I think now I understand what the distinction is, and I hope it will be clarified further as we get into chapter 4 and 5. Again, one of my criticisms of Sipser, that he doesn't spell things out enough. He's not a mathematician. Right. My current understanding, having got this far in his text, what's the difference between these two? If you're given a description if you're given the property that a string has to have for it to belong to a certain language, then if that string does have that property, then Turing machine that recognizes it will accept that string. So in a sense, the Turing machine, recognizes that this it has the ability to detect and to notice, if you like, that this string does have that property, because it will see that string does have that property. So it will accept the string. Now the thing is about recognizers, Turing machines that recognize, is there are three possibilities, three ways they can behave. Now this is a bit of revision. Recognizers can accept a string, they can reject a string, and the machine can loop. So they neither accept nor reject the string, and they just go on forever. Looping means not stopping, not halting. Right? To halt, you halt if you either accept or reject. Okay, the difference. So now a decider does not have that third option. Deciding machines do not loop. Right? They either accept or they reject, and that's it. There are only two possibilities for them. So in other words, the essential difference between a decider and a recognizer is that the decider does not loop. Or put another way, there's a possibility that a recognizer could loop. Okay? So when we're trying to show that some language is not decidable, think about it, what's going on? So if a language is not decidable, what does that mean? Well, that means the strings in it could... so the Turing machine that's working on the strings, it's possible that that Turing machine loops, and that there is no decider. So there might be a recognizer. You may have recognizers. So if these strings do have the property that defines the set, so you could have a set of members in the set that can be recognized by a Turing machine, but there may be no Turing machine, no algorithm, in other words, that can decide it. Right? So in other words, there's a possibility that certain strings in that, or certain strings, cannot be decided. In other words, you put any Turing machine on them, and those strings will cause that machine to loop. Right? It's a possibility. So if you can show then, and this is my interpretation now, if you can show then that there is no Turing machine, that there's no decider, right? So there's no Turing machine that will either halt, that will halt. In other words, it will either accept or reject for all strings. So it will accept the strings that belong to the language, and it will reject the strings that do not belong to the language. That's my understanding. I hope that clarifies things a bit more, because Sipser doesn't spell it out too well. I'm somewhat critical. All right. Okay. So Hilbert's 10th question is, given this language D, right? So it's a set of P where P has the property that it's a polynomial with an integral root. Okay? It's a set of all such polynomials. And Hilbert's 10th problem is asking whether language D is decidable, not recognizable. Right? Decidable means yes or no. this language D, all its strings can be detected, and all the strings not in that set can be rejected. Is there such a Turing machine that can do that? Is there such a decider, like a Turing machine decider for that language? The answer is no. Right? Okay, but you can show that D is Turing recognizable. So in other words, if this member P that it does have an integral root. If it does have an integral, then there is a Turing machine that will notice that. It'll find, it will observe that string. Now I'm sort of getting ahead a bit. That string, in a sense, represents the polynomial equation, or the polynomial. I'm jumping ahead, like the last session, we're talking about representations of polynomials and such like, putting them in the form of strings, and those strings then enter the Turing machine, and the Turing machine then does its work. So we will simplify things a bit now, and take a concrete example of a polynomial, and this time with just one variable, and then we'll use it to illustrate what we've been talking about on a decidable language. We're still getting into this kind of distinction, the idea that certain problems are just not decidable. There's just no decider. There's no Turing machine that for all strings just accepts the ones that do belong to the set and rejects all the others. There's just